Hello everyone, I am Monica from the Department of Computer Science Engineering. Today I am going to explain about hydrolysis and water resource engineering. This field focus how we manage water and how it moves, and we design systems that help us water safely and efficiently. Let's start the presentation. In this presentation it contains 5. One is foundation and hydrolysis, systems and resource and future. First one, foundation. Foundations of water engineering. It covers the 2 points, 2 main areas. Definition of hydrolysis. Hydrolysis is the study of fluids in motion, focusing on the principles governing the behavior of water in pipes, channels and other engineered systems. Hydrolysis means this is the study of water when it is moving in pipes and channels and rivers, etc. Definition of water resource engineering. Water resource engineering deals with the management and development of water supplies, including surface water, groundwater, and the infrastructure and needed to store, convey, and distribute water. Water resource engineering means about managing water sources such as rivers, lakes, dams, groundwaters, reservoirs, etc. Role in safe water supply. Ensures the availability of clean water for drinking, agriculture and industrial use through the design and operation of water treatment plants and distribution networks. Support for sustainable development. Contribute to sustainable development by balancing water use with environmental protection and supporting ecosystem and mitigating the impact of climate change. Water energy help us to make sure people for drinking clean water for farming and industries, and it also supports for sustainable development by protecting the environment and helping us to deal with the climate change. Hydrologic cycle and system components. It is the another part of it is very important, which is the natural movement of water from rain to oceans and again it back into the atmosphere. Engineers sometimes it change the cycle by constructing the dams, reservoirs, canals, etc. The hydrologic cycle describe the continuous movement of water on the above and below the surface of the earth, starting from the precipitation and ending with the evaporation. System components. In system components include surface water bodies like waters, rivers, lakes, groundwater, the atmosphere and the oceans, each playing a crucial role in water storage and transfer. Engineering inventions. Engineering inventions such as dams, reservoirs and irrigation systems alter the natural hydrologic cycle to meet human needs, often with significant environment impacts. Next, hydrolysis. Hydrolysis uses the science to understand how water flow. There are few key ideas. We also look at flows, continuity, energy and momentum principles. First one, content or conservation of mass. The continuity equation ensures that the mass entering a system equal the mass leaving it, fundamental for analyzing pipe network and open channel flows. Next, energy and moment equation. The Bernoulli equation describes he clearly explain about the equation, and that we understand that the conservation of energy in fluid flow, while the momentum equation helps analyzes forces and flow behaviors in hydraulic structure like sluice gates. Flow regimes, losses and roughness effects. Flow regimes. Flow regimes includes laminar and turbulent flow as well as subcritical and supercritical conditions, each characterized by specific flow behaviors and equations. Here regimes means how water behaves. Flow regimes includes laminars. Here laminars means which contain a smooth, and turbulent flow means it consists rough and mixed. Next, Reynolds and Freud's and Mach numbers. Reynolds number distinguishes between laminar and turbulent flow, and Freud numbers indicates subcritical or supercritical conditions, and Mach numbers is relevant for high speed flows. Friction losses. Friction losses in pipes are calculated using the Darcy-Weisbach equation, while the Manning formula is used for open channel flows and considering factors like roughness and slopes. Finally, engineers must consider friction losses by using the Darcy-Weisbach equation. Next one, roughness effect. Roughness, height and Reynolds number influence the energy dissipation in flows and affecting the design of channels and pipes to ensure efficient water and convenience. Third one is systems. Water engineering also deals with the systems that move water into pipe networking and pump station designs. One of the most important, like pipe networking, includes Hardy-Cross method. This method is used to analyze pipe networks by balancing head losses and flow in loops, ensuring accurate hydraulic performance. Next one is pump station designs. Pump station design involves matchings and pump curves with system curves to determine optimal operating points and considering factors like cavitation and energy efficiency. Next, we are discussing about the economic pipe sizing balance. Initial cost is with long-term operational expenses and ensuring the reliable water supply, and while minimizing the financial environmental impacts. Next, open channel pressures and conductive flows. Flow equations. Open channel flows are governed by equations for uniform, gradually varied or rapidly varied flow, while pressure conducts flow principle of pressure flow dynamics. Second one is hydraulic jump and waves. Hydraulic jumps means that open channels when supercritical flow transition to subcritical flow. Next one is resources. Surface and groundwater yield assessment. Here yield assessment means surface and groundwater yield assessment involves modeling rainfall runoff process, analyzing reservoir storage and implementation, and ensuring sustainable abstraction to meet long-term water demands. Reservoir planning and dam hydrolysis. Reservoir planning means that includes capacity, yield, duration analysis to balance water supply, storage and environmental flow requirements and ensuring long-term sustainable. Dam hydrolysis. Dam hydrolysis focus on spillway sizing, outlet works and designs and settlement management to ensure safe and efficient operations of reservoirs while minimizing environmental impacts. Fifth one, future. Climate change and integrated water management. Climate change impacts. Climate change alters precipitation patterns, increases extremes events and affects water availability and requiring adaptive strategies for water managers. Smart monitoring and emerging technologies. Smart monitoring like using T-sensor satellites to provide real-time data on water levels, flow rates and qualities, etc. AI-based forecasting. AI-based demands forecasting improves the accuracy of water usage predictions, allowing for better planning and allocation of water resource. Next, digital twins. Digital twins means creates visual replaces of water systems and enabling the detailed, simultaneous and predictive maintenance to enhance system and reliability and efficiency. Next, controlled automations. SCADA means automation improvements that control of canals and pipelines. System improves water distribution's efficiency and reduces operational cost and enhances overall system performance.